Okay, good afternoon to everyone. So we will start our class. Because there are some of your friend actually is asking on the previous topics, the two position synthesis and so on. So maybe we have some recap on it. So let us look at the asked. The questions being asked is actually, just a second. The question asked is actually, let us look at this. It's asking what is the difference between the rocker output and the coupler output. As what we seen before, maybe we go to any 4-bar linkage. So for example, this one, right? For example, this example. So this bar in our text, this is normally referring to the crank. This is coupler, and this is rocker. So what does it mean when we have 2-point synthesis? Is for rocker means that we want this rocker to move at the two desired position. So for example, maybe from here to here. So we want you to move it there, right? So that's why we are based on these two position, okay, and design the linkage, right? But then if we come to the coupler output, means we will focus on this, right? So how we want this bar to move, right? Maybe we can come back here. So that's why you can see that actually this is the link 4. So it will move from this red color line to the green color line here. So it will move this way, back and forth. Right, so that's why link 4 we actually referring to rocker. So we call it rocker output. Right? So that's why how we are based on this rocker and design the rest of the linkage. So this is the same. This is the rocker, and this is the coupler. So that's why the output is at the rocker. So we call it rocker output. So now we see this is a coupler output. So as I mentioned just now, this is our crank. Normally we refer to crank. This is coupler. And this one is the rocker. Okay. So that's why now you see that the movement is from this one C1 D1 to C2 D2. So it's the movement of the coupler. That's why we should say there's a coupler output. So see, same as here. This is a coupler. This is a rocker. So this is a coupler. That's why this is also a coupler output. Okay. Then another question is someone very sharp eyes. They see this link 6. Right? He asked me where is the link 6. So actually, for this problem, we are trying to find the motion of this C1 D1 to the where is my C2 D2? It should be here. C2 D2 and then C3 D3. So we want this motion, right? So we will form this design and then we get the linkage here. We know that this linkage will be moving from this line all the way to this line. So if you come back to the previous 2 slides, this is the part we are working on, right? So that's why we can further, because this is only the linkage. So we have 1, 2, 3, and also the base is the ground is ground link. This is link 1. So we have ground link 1. This one, if we covered this part, we covered it. So this one form a 4-bar linkage. So we have this link, sorry, this link 1, link 2, link 3, link 4. So because now the link 1, sorry, the link 2 here, it will not do a rotation. So if we are going to drive this mechanism with a motor, then we have to add in the additional, what we call it, the driver link. So that's why we have to build this linkage. So if you look carefully, this part is exactly same as the first one we do. Okay, so it's the same thing. Okay, so that's why your link can be more than 4. Okay, so it depends on anything on how you want to drive the link. Okay, so as I mentioned before, in industry, so either you drive it with a motor, then you need this mechanism, or else what you have to do is you can just put a hydraulic cylinder to move in and out from these two positions. Then it will still serve this motion. Right? So it's depending on the application. So this is some questions that your coursemates actually ask. Okay. So then we'll continue our class. So we have 120 students now. My attendance is 112, so make sure you take your attendance. So then we'll move to our class on position analysis. So sometimes you may notice why every time I share the screen, there will be a bit of stuck, because I actually have turned on I have two screens, so I try to turn on the Microsoft Team on another screen so that anyone have questions, you can type in so I can see. Right? If not, I can only see my PowerPoint slide. Right? So we are in the position analysis here. Okay. So just to recap, so this is a 4-bar linkage. So we have link 1 here, link 2, link 3, link 4. So this is one of the position. Because when you start to rotate it, so your linkage can also look like this: link 1, link 2, link 3, link 4. So it depending on how you arrange your linkage, how you design your linkage. Okay. So I also, just to recap, I also emphasize to you the reference point somehow is a bit confused, but we follow the textbook. So you have to make sure that link 2 is based on this O2. The information for link 3 is based on this point A, or we call it the local non-rotating coordinate system, LNCS. And then the link 4 is based on this point 04. So these are the important things you have to keep in your mind. Right? Where is the reference? So all these formulas is derived according to the reference point we set. Where do we stop? So I believe we stop here. That we calculate all the dimensions and also the angles. So that's why you will find out that your theta 2 is measured from this horizontal x line to there. This is theta 2. Theta 3 will be measured from here to there. So we have theta 3. And then theta 4 is from here to there. So we have our theta 4. Right? So this is the formulas we can use. So now if we look at the vector loop of linkages, okay, so we can actually representing the the coordinate system using a polar form or the Cartesian form. So we can have either of these. So polar form will be in terms of the radius and the angle. Cartesian form will be in the x and the y component. So you will see that the I hat here is referring to the x coordinate system. And then the y, sorry. The j is referring to the y coordinate. So when we are in the rotation, that's why then you will find k. Right? K is what we call the z-axis. Right? So this is how we can write it in the vector form, in the Cartesian format. So this is another way of writing it, same as this one. Right? Sometimes they will just write it in so-called imaginary format, numbers format. So here we call it the Euler identity, which we have E j theta is equal to cos theta plus minus. So it's referring to this one, j sine theta, right? So that's why this is exchangeable between these two. Right? So you can exchange your polar form to Cartesian and the other way around. So if you look at the vector loop equations, okay, so what happened here is that if you can see the arrow, so I have this R2 and R3, it will go to point B. So same thing happen is I can also say that in order from O2 to point B, go from O2 to point B, I can also go from this direction, which is the R1, and then go to here, which is the R4. Okay? That's why if you take the green path minus the yellow path, then it will be equal to 0. So this is how where you get the R2 plus R3 minus R4 minus R1, then it will be equal to 0. Or if you want to write it different way, that's why there's a lot of way you can writing it. So I can say R2 plus R3 is equal to R4 plus R1. So it's the same. Okay? So the other way of writing it is according to the link notation. So R2 is actually RA, R3 is actually RBA, R4 is actually RBO4, and then R1 is actually RO4. So means this one. This is R. This one we can also mention this is RO4. This is RBO4. This is RAB. This is RA. Okay. So it's depend on which notation you want to use. So if you substitute the complex numbers, because this is vectors, it consists of the magnitude and the direction. So if you substitute the complex numbers into these position vectors, so that's why we will get this all these numbers here. So what we have here now is we have A, and then we have an angle of theta 2. So that's why A theta 2, and then we have B and the angle. So we have B theta 3. Okay. Then we have C and theta 4. So C and theta 4. So we also have D and the theta 1. So what is the theta 1? So basically theta 1 is also measured from this x-axis, so it will be 0 in this case. Right? So in this case, theta 1 is 0. Right? So E0 you will get 1. Right? So it's not 0. So to solve the polar form, we must substitute the Euler equivalence. So then now we can expand this into xy component, right? So we have xy component here, right? So we can then, in order to solve it, then we will solve the real and imaginary part separately. We set both of them to 0. So this is what we always do. We set x equal to 0, y equal to 0. Then we can find the value, right? We can calculate the position, as long as we are given uh, uh, the basic information for the questions. For example, we are given the 3 links, so we can easily find the 4th link position in this case. So this is the real part, right? So we just break down from these equations. So we take all the costs, right? And then you can also, for the y component, then we take all the sine component, right? So that's why the imaginary, the j, can be divided out. So it will disappear from the equation. So we will get this function, right? So based on this, then we can now solve for theta 3 and theta 4, right? So theta 3 and theta 4. So we can find the angles. So what happened here is basically, let me see. This is all the relation between the angles. So now square both sides of the equation and add them together, right? Mean that you square this one and this one, then you add them together, right? So that's why you've got b square sine theta 3 square plus cos theta 3 square. And then the left hand side we also square and then add them together. So note that the quantity in parentheses of the left side is equal to 1. So then we can eliminating the theta 3. Okay. So do you understand this? So basically this one, because we have relation, so that's why this part, right? This part here will be equal to 1, so it will disappear from our equation. So we left with the information here. So normally the theta 2 is given, so then we can actually find the theta 4, or basically if it, depending on which parameter is given. So most of the times in this kind of question is that we will give you the information of the crank, right? And then the length of the rocker. So then you have to find the so-called the angle of the rocker or the link form, okay? So if we expand this expression, right? So I mean expand this expression, so we will get these formulas here, right? Divided through by 2AC, and then we try to rearrange, so we will get this the formula in the red color rectangle here. So we will continue because this is derivation. You can work out slowly to see where is this formula, how is this formula applied, right? So now he even put a constant k1, k2, k3 to simplify the equation. So k1 equal to d over a, k2 equal to d over c, and then k3 is equal to the equations here. So a square minus b square plus c square plus d square divided by 2ac. So the equation will be simplified with this constant k1, k2, and k3. So again, then we substitute the identity. So this is again from the trigonometry function. So then we can further reduce the term in the equations. So substitute the half angle identity, okay, which will convert the sine theta 4 and cos theta 4 terms into the tangent 4. So again, this is again from the trigonometry function. Maybe I will share the documents to you later, right, on the so that you don't have to find the trigonometry formulas. So then you can compare to these solutions to see how it actually applies. Right? So from here, then basically we will be able to then find the theta 4. So this result in the following simplified form, where the link length and known input value theta 2 terms has been collected as a constant ABC. So again, it is simplified that in 4. So we'll get this. So means as long as you know the link length and the theta 2, so you can substitute into here in order to get your A, B, and C. So then you can substitute back into the so you can substitute back into the bottom here, the rectangle box, to get the theta 4. Okay. So this is how we find theta 4, but maybe over here you will be a bit confused because there is too many derivations. Okay. So if you are interested, or if you like trigonometry, basically, then this will be very easy for you. Okay. So then we can find, just now we find the theta 4, so now we find the theta 3. Okay, so similar way of doing the theta 4. So we have these two equations. Okay. So squaring it and adding them together. So again, you square the both equation here. You square it, and then you add them together. So that's where you get. And then also now he applied. So you can see that now he labeled this K4 and K5 because K1 to K3 is being used to find the theta 4. So this is K4 and K5 with this constant, not constant, this formula is given. Okay, so basically this is all the link length. So with this link length, then we can continue to find it. So again, so because this formula is long, so it will be further reduced to DEF. Again, this DEF can be found with the link length information and the theta 2. Right? So we will be able to find DEF that actually can substitute into here or into these formulas to find the theta 3. Right? So here mentioned as with the angle theta 4, this also has two solutions, corresponding to the cross and open circuit of the linkage. So now you will see that there is a plus minus here. So that's why I will mention theta 3.1 or theta 3.2. Same as this theta 4.1 and theta 4.2, because there is a plus minus here. So in a graphical way, what it is representing so at the beginning of the slide, so we have this. Right, so basically, actually, with the same, if you can see here, with the same theta 2 and the link length info, so means that the A, B, C, D is given, and also theta 2 is given. There is two possibility of the arrangement of the link. So one of it is the red color one. The other one is the green color one. That's why your if you measure the angles, for example, the theta 4 here, so we have two different angles, right? That is where we get the plus minus the function. So same happen to the theta 3, yeah. So we have one here, so the other one will be basically here. So this will be theta 3 prime, so sometimes I call it prime. So this is that's the way we get the different angles for theta 3 and theta 4, right? So this actually is what really happen in linkage. So you get the plus minus. There is the two angles there, same as the theta 3 here. Okay. So to understand it better, maybe we look at the example here. So we have a very same setup 4-bar linkage here. So given a 4-bar linkage with the link length, so you can see that he gives L1. So you remember L1 is D, yeah, it's not A, yeah. L1 is D, right? Is this one D? So it's 100 millimeter. L2 is the A, 40 millimeters, and then L3 is a B over here, 120 millimeters. L4 is C, 80 millimeters, and then theta 2 is 40 degrees. So we try to find all the possible value for theta 3 and theta 4. So it means that basically we will have theta 3 and theta 3 prime, right? Theta 4 and theta 4 prime. So we have the two different angles. So one is the open loop and one is the cross. One is an open circuit and one is a cross circuit. Okay. So that's how you see a lot of derivation. So basically, if you want to solve it, so we can straight away use this K1, K2, K3. Yeah. So for this trimester, you have less to worry about all these formulas, because all your midterm, your final assessment are all open books. Okay. So you don't have to worry which one to remember and so on. So you just make a note that you can find the K1, K2, K3, K4, K5. You still have K4, K5 to find the theta 3. Yeah. So here we have K1 is D over A, so we can just calculate. It's 2.5. K2 is D over C, so we get 1.25. K3 is with all these equations here. So if we substitute all the A, B, C, D into the equation, so we get this 0.562. So again, after we get all the K, then we can find this A, B, C, yeah, okay, using the information we have. So theta 2 given 40 degrees. So we have K1 we find 2.5, K2 1.25. Again, theta 2 is 40. K3 is 0.562. So you'll get this A is minus 2.129. And then B is given with this formula, so substitute the 40 degrees, so we get minus 1.286. And then C, we have the formulas here, so substitute all the value we have calculated, so we get 1.339. So with this, then we can find the theta 4, but then we will find both the open and the cross circuit configuration. So we will get this 50.733 and minus 90 minus 98.01. Okay. But when you have this information, right, so you can always sketch it out. Where is this angle? So for example, we use back this one. So for example, first one is 50. What is the value? 57.33. So if this is 57, it will not be there. So maybe it's better for me to draw a new one. Draw it. It's over here actually. Then we don't have to draw. So the first angle is 57.33. So when the second angle, when you calculate, you get negative. So it means that we are measuring from X also, but in the clockwise direction. So that's why you have the negative here. Okay? The positive is measuring counterclockwise. The negative is measure clockwise. So we get 98.01, so which is at this position, the theta 4. Then we can continue to calculate the K4 and K5. Okay, so we get these two values, K4 and K5. So then we can calculate the DEF that can be put into this formula here, the theta 3. So again, we have open circuit and the cross circuit angle because of the minus and plus here, right? So we get 20.3 and minus 60.98. So visualize it. So 20.3 is here, minus 60.98. As I mentioned, when you get minus, it means that again from the horizontal line, we measure clockwise, right? So that's why we get this. So the open circuit is referring to this yellow orange line. Okay, so this is the open circuit with the theta 3 is 20.3, theta 4 is 57.33. Yeah. But then for the cross circuit, so we still have this theta 2 is 40 degree. Yeah. So this is given. And then the link 3 will be in this direction because of the minus 60.98, and then link 4 will be here. So we call this is written there. We call this cross circuit. But then for this one we call it open circuit, right? So this is at two different setup, right? Maybe I can show you one of it. Let me turn off my sharing slides and then turn on the video. Right, so this is the I should show it this way. So if you look at here, so in the bottom part here, I consider that is ground link, and then this is link 2, link 3, link 4. So open circuit means now we have it this way. So if you see that if I turn, I fix my link 1. If I turn, right, I got my link 2 to do the rotation. Okay, so my link 4 here is rocking at the top side there. But what happened is, let me see whether I can remove or I can, I crack my linkage. If I put it downward like this, right, then this will be the cross circuit. So again, this is my ground now. This is my link 4 and my link 2 will be on top here. So if you rotate, so it will do the bottom part, okay, over here instead of the upper. So that's why here we call it cross, because if you notice that this is crossing down outward. So that's why you can have two set up here. Okay, this one is a 4-bar linkage. So what happens if we are in the 4-bar slider? Okay. What happens if we are on the 4-bar sliders? So you can see that 4-bar slider, we still have the link 2 here. We still have the link 2, and then link 3. But then our link 4 is here. This is my link 4. So the sliding block is my link 4. So this link 4 will do movement at the at this horizontal position. So the let me erase this. So the difference here is that now if you look at the D, this D now is not a constant value. This D now is moving, right? Because this point is moving back and forth because of the movement of the sliders. So we have A, B is fixed. So C, you can just show that that is a virtual link that we have, which is a C here, which is the distance between the O2 to the or by right. For the instant, we will have O4 here, O4 to B. That's why I call it link C. But this whole link C is moving back and forth in this direction. That's why the D will be changing. So a few things here. Here we call it offset. So again, the angle θ2 is measured from here. And then θ3 is again measured from here. So this is the θ4. So for the vector loop equations, so let me create. So it depending on how you can define it. So in this case, you define this is A or R2. Then we have the R1, R4, and then meeting it here. Sorry, θ3 just now I mentioned wrongly. So we have R1, R4, and R3. So for sliders, it is reference move to point B here. So the θ3 will be this one. So you have to be quite how to say alert on this. So instead of the measure from point A, measure from point B, your θ3. That's why then when we build these vectors, it will go from here R1, and from here R4, and then go down R3, and then they will meet at point A there. So that's why when you write your R2 is equal to R1 plus R4 plus R3. So if you rearrange it, that's where you get this equation, R2 minus R3 minus R4 minus R1 equal to 0. So again, we can substitute the complex numbers into the formulas and then apply the Euler equivalent to get basically the x and y component. So again, we separate it into the real and imaginary components. So this is the real component, and we have the imaginary parts. So again, θ1 is 0. So that is where you get your cos θ1 is 1. So but then sin θ1 is 0. That's why the d will be disappear from your imaginary part. So now the other interesting parts here is now we have the θ4 is 90 degrees. So this one, this is 90 degrees. But then the d is changing based on the movement of the other two links, the link 2 and the link 3. So the d will actually change. Okay. So from here we can, based on all this information, we can calculate again the angle of link tree. Right. So highlight again, angle is measured from here. So you can see that one of it, the angle we can have it here with this setup. So we still get two different angles. Let me see. Oh. Let me see whether we get the example. Give me a second, so I will draw. I draw the what we call it, the cross setup. Okay, so that is the two setup here. Maybe we turn on. We put up the screen. Okay. So just now the one we have is that we have the angle here, the link tool, and then go to the sliders, like this. So we have the link 2 and link 3 here. So with the angle of theta 2, okay. Because with the same information given, actually I can draw the other one. I can still have the same offset, but now my slider is at this position. I draw it slightly too far. My slider can now be in this position, and then my link tree can be this way. Okay. So if you look at it carefully, I can have the same offset. I can have the same link to length, same theta 2, same link tree. This length and the left and the right, the link tree is the same, but now I place my slider on the left hand side. So then your theta 3 will be measured from this point. So your theta 3 now will be like that. So this is theta 3 prime. So then this one, I transfer the color. So this will be my theta 3. So that's why you also get two theta 3 as well. So we will call this open circuit. And then this one is the cross circuit. Right? So we can have two. Right? So same thing as it does out the 4-bar linkage. We can have all the information, same information for the link length and the theta 2 angle, but then we can have two different setups. So same as this 4-bar sliders, we can also have all the information is the same, but then we can set up it in two different ways. Okay. And so that's why we have a theta 3 1, theta 3 2. Okay. So now we can look at the one example here. So we get the 4-bar crank slider linkage. So again, it gives us A, B, C with that. right? Because d is a function, so that's why d is not given. D is a function here, okay? A cos theta 2 minus b cos theta 3, yeah? So given theta 2 is 60 degrees, so we can find all the possible way. That's why we have open circuit and the cross circuit, and also the slider position. Yeah? So we have the formulas, yeah, that we derived just now. So then we can substitute the theta 2 A, C, and B. So we get 152.91 degrees. Right, so to calculate the D, we use these formulas. So we substitute the A, theta 2, B, and theta 3, yeah, that we calculate from here. Okay, so we get 126.84. So now we have another formula for theta 3, which actually, if you look carefully, is just this one and this one. Right, the addition of minus and also the plus pi there. Okay? So we get the angle is 27.09. Okay, so once we get that theta 3, so we can substitute into this equation. Sorry, someone asked why the angle that larger than 90 degree is defined as cross angle. Maybe I will go back to that while we finish this one first. So we substitute into this d here, so we will get the distance d is in the minus. That's what we have just now. My slide is disappear. What we have just now is on the opposite side. So if you look at this, you can see offset is negative 20. Yeah. So what happened here is, if I sketch it, I have 60 degree of link 2. Then this is my O2. So now my offset is negative 20 mm. So what happened here is, now if you see that my link 3 will look like this. Okay, let me see whether I have. So that's why if we measure the angle, this angle theta 3 is 152.91. Okay, so there is another possibility that my slider is at this side, so I can also connect it this way. Okay, so that's why when we calculated the theta 3, then we get this one is 27.09 degree. Okay, so that's where we get the two different setup. Right, so as your friend asked, why the angle that larger than 90 degree is defined as cross angle. So basically we are not really looking at what angle you get. It's more like how the setup, for example this one, how the setup is that open angle means that everything is on one side, right? Cross angle means it will be crossing the link here, right? The axis here, axis, right? Similar to this one, right? Open angle means it will be like that. The other one it will go opposite way, okay, to this side. Okay? So there is a cross. Okay? It will crossing the link, the axis, the O2 axis. Okay. Okay, well, I will stop here because today I want to brief you a bit on the assignment. So I have just posted the assignment into Weibo as well as the chat column here in the meeting, so you can download it. So the other thing is maybe we can have a look on into it. So just a quick one. We look at it. Okay, so even though now we are in the so-called online teaching and learning, so but this assignment because it's slightly lengthy, because now the marks contributed is quite high, which is 30%. Maybe I double check. Hopefully I don't do it wrongly. So if you look at our lecture 00 there, so the assignment is 30%, midterm is 15%, practical laboratory is 15%, and then the final assessment is 40%. So now the assignment is 30% out of your whole course. And also the assignment is actually in our OBE, outcome-based education. So the assignment is linked to the 3 outcome. So we have question 1 actually linked to outcome 3, question 2 is linked to outcome 4, and then question 3 is linked to the outcome 5. So 3, 4, 5. So that's why we will have questions on the balancing. So this is more straightforward. This is just a calculation, how we can balance this steel roller. Right? So the information is given. So you can download the lecture notes and look at how to solve it, as well as the textbooks. Okay, so the how many people in the assignment I will brief later. So we go through the question. So you have to discuss on the methodology of measuring and correcting imbalance. So maybe you can give an example like the car tires balancing, car wheels balancing. So how they do it, but it cannot be too layman term. So you have to explain what the machine do, right? I believe majority of you may actually seen how the technician in the workshops do the tires balancing. If not, then you can go and watch in the YouTube. So there is a methodology on how we can do the measuring of the unbalance and then do the correction of this balance. Even now, if you buy a China ceiling fan, also they ask you to do balancing yourself. They always give you 2 pieces of magnetic weight, so to fine tune the fan balancing. Okay? I find very challenging. Okay? That one. Because that method is trial and error for the fan, China flat ceiling fan. Right? But for cars, for this steel roller, because it could be steel roller used in the steel mill and so on. So you must balance it. If not, then your bearings and your drive shaft, all this will have a huge impact or wear and tear in the system. Then question 2 is more like a write up from a reading. So most of the car in the market is actually 4 cylinders, but we are seeing that more and more car is going for 3 cylinders because of the emission restriction, emission rules, right, implied to the industries, right? But 4 cylinders, majority is still 4 cylinders engines. So you try to explain the construction of the engine, right? So you can find any engines sketch drawings, then you can explain how is the construction of it, right? So there are a few main parts. So over here in the something related to mechanics of machine, which is the crankshaft, the connecting rod, the piston, right? And then you after that you can do a simple comparison with the different type of engine, right? So even same inline engines, we have one, we have two, because one we don't call it inline, we just call it single cylinders engine. Right? We have 2, 3, 4, 5, 6, but I hardly see 7 cylinders. Then 8 cylinders, 9 cylinders also not really that common. And then 10 cylinders, and then 12 cylinders. Right? So you will see 18 cylinders or even 24 cylinders. So in the market. But normally when we go more than 8 or more than 6, normally the engines will become a V configuration. So we call it V engines. Right? So that's why you see some cars say they are V8 engine, V12 engine, V10 engines. But if you go to offshore platform, then you might see a V24 engine. So that is a generator diesel engine. That could be V24. Right? And you were surprised that you will see the engine is running on the engine brand Rolls-Royce. Right? So that's why oil rig somehow is expensive. They may be driven by a Rolls-Royce, few Rolls-Royce engine. So if you go to the engine room in the oil rig, there are few of it. So then question 3 is on the gear. Question 2, there is another part you have to discuss is on the problem that you face. For example, shaking force, shaking torque, shaking moment. And then what are the possible solutions? For example, the Nakamura balancing and so on. So you can discuss in these questions. So question 3 is on the gear. So we have to design a compound gear with the exact reduction of the speed from 900 RPM to 72 revolution per hour. So you have to do some conversion here. And then remember the pressure angle for the gear is 25 degrees, and you have to use 25 degrees. So the question B here is to write some discussion on this torque converter. So a lot of automatic car has this torque converter, right? And then what is a continuously variable transmission, the CVT, that you can find in a lot of cars nowadays. The first manufacturer uses a lot is the Nissan from Japan. And then also the differential gear that you can find in the car. All right. So you can team up to six people. Because there is 3 questions, so I don't limit to 5, I limit to 6. So and up to can do 1 question. But I highly encourage you share your solution with your group mate. Don't keep it for yourself. Okay? Then submit in the PDF file. In the PDF format to the Weber. I also created the link. Right? So remember, so each of the questions you need to have this format. So I will assess in terms of the presentation. Right? You still have to describe your problems. Right? You may take my questions and then you rephrase into a description matter. Right? Description. My one is a question, so you can put it in the description what you want to solve. And then methodology, please remember, put out all your working sheet. You can write it down and scan and put in a proper single PDF file. And then result and discussion, also summary and conclusion. So if there is any other reference, you also put it down. So each question the full mark is 100. So 3 questions add together divided by 3, then it will become your 100%. Or I forgot. It should be multiplied with again a 30% there. So that will be your final assignment. So beside this, we're running out of time. Beside this, you please use the cover page I prepare. Okay? I also send it to you. So just put down your student name and then you can start with the report. What else? Last thing. There's basically no page limit. But don't give me 100 pages. Okay? So there is no minimum. I always say that I set it to 6. If minimum, you can do it solo. That is my, if you attend my class before, I always say this. I don't stop people to work alone. That is up to your own preferences. And the other one is on the Weber. So I already uploaded it here over here. Okay, the group assignment and the cover page. So the submission is on 19 August. So I give you, should be more than enough. Initially, I think the plan is you submit on week 8. So now I move all the way to week 10, which is 19 August. Okay. So any more questions from you guys? No. So page limits, but I click. Page limit is, I'm not sure how long you do your, if you write your working, you can write it far away, then you can have many pages. So as long as page limit, maybe keep it within 20, 20 to 30, right? Depending on how big is your diagram you put in and so on. Right? So if no questions, I think, are you sure? Someone say 20, 30 not enough. Our PM pictures. Say 20, 30 not enough. I leave it to you, but my suggestion maybe 20 pages plus minus over there, it will be very good. Okay. So I think we have to stop now. I have already eat up some of your other time. So always can just 3 people. Yes, you can form 3 people. Right? I only set the maximum 6. So whatever number you want between 1 to 6 is up to you. Okay. So I always, if you have any questions, you can ask me. Some of you already asked me in the chat, and then I hope that it actually helped. It's also good that you ask me, then I can brief the whole class. And some people may feel shy to ask. So I always appreciate the student who ask questions. Because for me, I've been teaching this subject for I think 5 years. So I may not see the problem that you see. Okay. Thank you so much. So remember to take your attendance on the top there, submitting the vote. Okay. So those students who haven't registered, make sure you register the subjects. Thank you. See you. Bye.